Now looking at this circuit, some resistors are in series with some other resistors. Some say resistors are in parallel with some other resistors. How do we approach this? The best way to do is to look from the end. But before we even go to the end, let's look at the beginning first. This is our source of power. Current is going to flow out of this voltage source into this resistor 1 ohm. The current that is coming out of this voltage source is the same current flowing through 1 ohm. So you can say that 1 ohm is in series with the power source or the voltage source, because the same current that comes out of this guy, the same current flowing through 1 ohm. Now at this point, at this node, there is a splitting. Whatever the value of current that's flowing through 1 ohm splits at this node here. Part of it flows into I3, the other part flows into I1. So at this point now, you will see that resistor 1 ohm is in series with whatever happens at this point. Do you understand? This resistor 1 ohm is in series with every other thing here. Do you understand that I just said?
Yes.
Yeah, so resistor 1 ohm is in series with every other thing here. So now we have to investigate the remaining resistors at this other side. So now we can see that this is the end of the whole circuit. We don't have more branches or more resistors at the end. So we start from the end now. We look at 2 ohms and 3 ohms. There was a splitting that resulted to both of them. So you know both of them are connected in parallel. So we can just tell us that 2 ohm is parallel to 3 ohms. So we look at these ones together like this as a parallel combination. So 2 ohms resistor is connected to 3 ohms resistor. So to get the equivalence of that, you have R equivalent for 2 ohms and 3 ohms. 2 ohms is parallel to 3 ohms, and I told us in last class that you have product over sum. That's 2 times 3 over 2 plus 3, and that's 6 over 5, and that's 1.2 ohms. So this combination here, when we combine these two, the equivalence we will get is 1.2 ohms. So we can redraw our circuit. It's usually good practice to redraw your circuit so that you don't make a mistake. So that when you, in fact, if you get stuck, you can easily go back and check. So we have our 1 ohm resistor, but now we already have 1 resistor that is now the equivalent of these two. So we have 1 ohm here, and this one, which is already R equivalent, is equal to 1.2 ohms. Do you understand to this point?
Yes.
Now, so you can just see very easily that these two are connected in series. Why? Same current that flows out of the source will flow through 1 ohm. There's no splitting here. The same current is going to flow through this 1.2. So we can say that 1 ohm and 1.2 are in series. And you know, when we have series connection, all we do is just to sum up the individual resistance. So for these two now, which are in series, our R equivalent at this point will be equal to 1 ohm plus 1.2 ohms, and that will give us 2.2 ohms. So the equivalent resistance of this whole circuit, which is equal to the total resistance in this whole circuit after breaking it down, is 2.2 ohms. So to further draw this circuit, you can have something like this, just 1 resistor now, and that's 2.2 ohms, 12 volts. Do you understand that now? So now the question is saying we should find I1, I2, I3. We want to calculate the values of I1, I2, and I3. But before we can do that, we have to get our total total current flowing out of the source, which is I. And from Ohm's law, we know that V is equal to IR. Our V is 12 volts. Our I is what we're looking for. Our R graph is 2.2 ohms. So that means our I will be equal to 12 divided by 2.2, and that should give us what? That's 5.45, but you can confirm. Am I right? 5.45 amps. Don't forget to put your units. 5.45 amps. Is that what you got? Hello?
Yes.
Yes, 5.45. So our I is equal to 5.45 amps. So because my body is small, I will have to clean some things off. Let me clean all these points and leave the main circuit. I'm sure you understand to this point. Let me clean this one too, so that the circuit stands alone. So redrawing the circuit, we have this. Let me just redraw it so that everything looks neat again. So this is our 1 ohm resistor. We add 2 ohms resistor here. We add 3 ohms resistor here. And we're totally for I1, this is I2, and this is I3. Now I want to calculate the current I1. Since I1 is equal to the current coming out of the voltage source, so we can say I is equal to I1 and is equal to 5.45 amps. Do you agree with me? Hello?
Yes.
Hello?
Yes.
Yeah,
I
because
said yes.
okay, all right. So I is the current. Okay, you agree with me. So the next thing you want to calculate is R2, the I2. So to get I2 using the current division rule, using current division rule that states that I2 will be equal to R3 ohms. That is the resistor. This R3 ohms multiplied by I, that's the total I, divided by R2 ohms plus R3 ohms. So this is just to make it simple for you to understand what I'm saying. So to get this our value for I2, I2 will become R3 ohms, which is 3 ohms in our case. So 3 multiplied by I, which is 5.45, divided by the sum of the two parallel resistors. We use current divider rule when we're dealing with parallel connections. So the sum of these two parallel resistors, which will be 3 plus 2 or 2 plus 3. Okay, let me use 2 plus 3 because I am following this. This is 2 plus 3. And so our I2 will give us what now?
3.27.
3.27. Exactly.
Yes.
3.27 amps. And we can also use current division to get our I3. And that will just give us I times 2 over the sum. But a very easy way to do this, since you know this current was flowing into this node, I1 was coming inside the node, and this I2 and I3 splitted, I1 splitted into 2 to give I2 plus I3. We can just say that the sum of I2 and I3 will be equal to I1. So we can say that I1 is equal to I2 plus I3. And now we've gotten I1 and I2. So invariably I3 will be equal to I1 minus I2. And that will be 5.45 minus 3.27. And that should give us something like 2.18 amps.
Yes.
Yeah, 2.18 amps. So we've solved our question. I1 was equal to 5.45 amps. I2 gave us 3.27. And I3 is equal to 2.18 amps. And now let's even look at it, if it even makes sense. If 5.4 amps got here, normally current will prefer to flow through the path of least resistance. You can see that this 3 ohms is bigger than 2 ohms. So 3 ohms, current will, this 3 ohms is going to oppose more current. than these 2 ohms. So more current will flow through 2 ohms because it's a easier path to flow through. So when it gets here, you can see that 3.27 out of the 5 went through 2 ohms and 2.18 went through 3 ohms because of the value of the resistor of the resistors. So I'm sure with this, you understand how to analyze series and parallel circuits. Do you understand this example very well?
Yes.
So let me just quickly do one more that looks a little bit more complex. It has more networks, more resistor networks. Now this one is a little bit different. It has a dependent, of course, you know what a dependent current source is, and it has some values. It has the resistor value here, which is 30 ohms. Then we have another one here, which is 10 ohms. Then we have one here, which is 40 ohms. Then we have another one here, 4 ohms and 8 ohms. Now, the whole idea of this is just to make you get used to series and parallel networks. So now, of course, in every dependent current source, you have a voltage across. And the value of the current source is 12 amps. So we have 12 amps feeding this whole circuit. And the question is saying, find the value of V and the branch currents. Find the value of V and the branch current. I just hope I'll just solve to a point, maybe to this point, then I'll allow you to do the rest, or once you understand, we stop there. But for now, I just want you to get the concept. Now, this is 12 amps coming out of this source. When it gets to this point, of course, there's no obstruction. It is just the source connected directly to the system. When it gets here, there'll be a splitting. Part of it will flow here, another part will flow here. This one that flows here, the current that flows here will continue to this point, to this node. When it gets here, there'll be a splitting again. This one will come here, and this one will come here and flow to this part. So it's usually good to start your analysis from here. So you just look at it from this point. Looking at it from this point, you will see that these two are in what?
They are in series.
Exactly. These two are in series. So we have 4 and 8 in series. And so what that means is that the equivalence of these two, the R equivalent will be 4 plus 8, and that's 12 ohms. So as I said, it's good practice to withdraw. Let me just quickly go through the plane to withdraw again so that we don't get confused at some point. Once we are done getting our value, I'll clean everything up. So at this point, we have the 30 ohms still, 10 ohms, we have 40, but now we have 12 here, 12 ohms. So 12 ohms is the equivalence of these two resistors connected together in series. Now, there's a problem here. The problem now is that we want to analyze now these two. These two, are they in parallel or in series?
In series.
No, these two are in parallel. Why?
Okay, yeah, they meet.
Yeah, they meet at a node. Exactly. There's a splitting from this node to these 2 points. So these two are in parallel. So looking at these two, it's very important to understand these things. It's good to go and solve more problems after this class so that you'll be sure that you understand. So 40 ohms is in parallel with 12 ohms. And of course, the equivalence for that to be product over sum. I've said that before. So please just help me with that value. I'm working with your values, so just calculate it for.
It's 9.23.
Sir?
9.23.
That's 9.23.
Yes.
9.23 ohms. So this particular network parallel connection gave us the equivalence is 9.23 ohms. And of course, we just do this again for almost the last time. Then make it smaller. When we come here again, we have this, and we have this now. So this is my 12 amps. Okay, this is 30 ohms. This is 10 ohms. And now this is the equivalence of these two, which is 9.23. So now looking at it now, what can you say? Just help me, use your words to tell me which is in parallel, which is in series, or what do you think we should do next?
I think they are the 10 and the 9.23, they are in series.
Exactly. Because same current that flows through this is not branching anywhere, it keeps flowing through. So you are very correct. So these two are in series, and of course, that gives us an equivalent value of 10 plus 9.23, and that's 19.23 ohms. And so gradually, we're coming to the end of the whole puzzle. I just hope you can still see the board. And this is 30. And this is 19. So this is 19.23 that we just got here. And this is 30. Of course, this is 12 amps. So from this last part, it's obvious that when the current flows to this node, there's a splitting, this point and this point. So you just agree with that these two are in parallel, right?
I have a question.
Okay, please ask your question.
Once you added the 9.23 and the 10, how are you going to know which position it's supposed to be? Couldn't it be at that 10, that former 10 position as well?
Sorry? I didn't get you.
When you added the 9.23 and the 10,
yes,
how are you sure this is like the right position? Couldn't it be at where the 10 was before?
oh, it's the same thing. Now, if I put this 19.23 up here, it's still the same thing now. This is just a wire. It's just like I should just draw it back up here.
Okay.
You understand? I just do it because I don't have space to write anything here. It's the same thing. It's just a wire. There's no, even if I put it here, it's still the same parallel connection. It still splits into the two of them. You understand?
Okay.
Yeah, so the same thing. Yeah. All right. So at this point now, we know that these two are in parallel, and it's going to give us a particular equivalent resistance, which is going to be 30 times 19.23 over the sum 30 plus 19.23. So please help me with that value.
11.71.
11.71 ohms. So at this point, we've been able to solve till the point where we've gotten the total RT, the total resistance of the circuit. This circuit now, we're able to get the total resistance of the circuit, which is 11.71. So I think that's the beginning of our solution. Let me quickly. Sorry?
Nothing.
Okay, don't worry, I will solve everything. I'll just solve for the first two and leave you to solve the remaining one. So let me do this so that I don't tamper with all the drawings we've done. Let me just do all my solution at this corner here. Let me just do all my solutions here. I don't want to tamper with the circuits I've drawn so far. Just bear with me. I have a small board. So, so at this point, this is what we have. So invariably, what we have, the last circuit we have or we've gotten from all our solution is just a circuit that has one resistor, which is the total resistance of the whole circuit of this whole circuit, and that is 11.71 ohm. And this is 12 amps. So the question said you should calculate the value of V. Remember, there's a V here. That's what the question says. Find the value of V. And from Ohm's law, V is equal to IR. And we know our I to be equal to what? 12. And our R to be equal to 11.71. So you can just do the mass and get the voltage.
It is 140.52.
140.52 volts. So this is the voltage of this source here. So this, let's assume whether it's a battery or something, it gives us 140 volts DC with a current of 12 amps. So that is all that we've been able to interpret from all the solutions. But the question says we should find the branch currents and the branch currents. So at this point, you know that this is 12 amps flowing to this point. When it gets to this particular point here, there will be a splitting. A part of it will flow through 30, and the other part will flow through all these other guys here. All this other, it will continue at that point and keep splitting. So, okay, we'll be running out of time in no time. Let me just quickly. Okay, so let me quickly finish before the whole meeting goes off. So at this point, you have 12 amps flowing to this point. So it splits. A part of it goes into this 30 and the remaining continues. Now, where is that point where we have that split? That is here. You can look at it very well here. 12 amps was coming. A part of it went to 30. Then the remaining continued. Can you see it down here?
Yes.
You can see that the remaining continues into an equivalence of 19.23. So using current divider rule to get this the current of 30 ohms, we just get R equivalent, which is 19.23. Using current division rule, multiplied by the total current. What is total current? 12 over the sum of the resistors. That's 30 plus 19.23. So please just let me do this mass. So I'll get our current flowing through 30 ohms. I'll do this and I'll do.
I can't see very well.
Okay, you can't see. Okay, what I have here is actually 19.23 times 12 divided by 30 plus 19.23. So that will give us a value.
Divided by
the sum of 30 and 19.23. That's 30 plus 19.23.
$4.67.
Sir?
4.67.
4.67. 4.67. Of course, out of 12, the 12 amps was coming. It saw 30 ohms and it saw 19. More will rather flow through the 19 than 30. So 4 was able to flow through. So that's 4.67 amps. So the current here is going to be 4.67 amps. Now, to get the current that's flowing into this 19, okay, to get the current that is flowing into this 10, we have to first of all know the current flowing into the whole 19 that is flowing out of this point into everything. And to get that, that will just be 12. Let me do that up here. So to get I 10 ohms, which is equivalent to the I equivalent of 19.23. Do you understand what I'm doing here?
I think so.
Okay, let me just show you what I mean. We have 12 amps coming out of this point from the source, and then 4.67 as calculated came here. So there's a remaining current that continue flowing. That's what we want to calculate now. That's the current that flowed into the 19.23 equivalence. You understand?
Okay.
And to do that, since we know 12 came here, so 12 is equal to the sum of 4.67 plus the I 19.3. So I 19.23 is equal to 12 minus 4.67. This was that. And that's 7 point what? Are you there?
Hello?
Hello, are you there?
Yes.
12 minus 4.67. What is that?
That's 8. Sorry.
That's actually 7.33.
7.33. Yeah.
Exactly.
I made a mistake.
So 7.33 amps. 7.33 amps is coming into 19.23. That is the current that is at this point, this equivalent. And you know that this 19.23 represents everything here. Everything here, that's 19.23. So the point we're just trying to bring is that 12 amps was coming, 4.67 came here, then 7.33 amps continue the journey. And because this is a series network now, this 10 ohms in series, so we can just conclude that the current into 10 ohms is 7.33 amps. Do you agree?
Yes.
Yes. So 7.33 amps got to this point again before there was a new splitting. 7.33 amps got to this point before there's a new splitting. And that's what leads us to this point here. This point here. So at this point now, we have 7.33 amps. And there's a new splitting at this point. We have two resistors in parallel. I'm going to stop at, okay, in fact, that's all about the question. We're almost done with the whole question, so I can finish everything. So in less than, in a moment, this class will be over, this meeting will be over. So let me just please solve this. To get the I40 ohms, I40 ohms will give us 7.33 amps, which is the total, times the opposite, that's 12, which is the equivalent of what this one's here, over the sum of 40 plus 12. And what is that going to give us?
I'm coming in.
All right.
$1.69.
1.69. So this 1.69 amps. So what came into this place is 1.69 amps. Now to get what is leaving this 1.69, very simple. Since 7.33 came in, 1.69 left, what remains? So that will just give us,
Just minus it.
yes, exactly. So what is into this node, which is 12, this 12 ohms branch will be 7 minus 1.69. That's what?
5.63.
Minus,
63.
yes. 7.33 minus 1.69.
5.63.
Okay, 5.63 amps. So we can conclude that what came into this place now is 5.63 amps. So at this point, 1.69 amps came from this place. 7.33 came, 1.69 dropped here, and 1.69 amps was flowing through this 40 amps, 40 ohms. Then the remaining 5.63 amps continue the journey. And that's 5.63 is going to flow through the 4 ohms and also flow through the 8 ohms. Why? Because they are in series, same current flows through. So that way we've gotten everything. So we have 12 amps got this place. There was a split 4.67 and 7.33. If you sum these two, you get 12. Then this 7.33 continue flowing. When it got to this point, it saw a larger current resistance here, 40. It only dropped a little. It sent just only 1.6 amps could flow through the 40, while the larger part was able to flow through this network of 12, which is this. And so we've been able to solve this problem. So a good understanding of this makes life easy. So because we have been dealing so far with circuit that have just one source, either current source or voltage source, That's why I'm using this approach of series and parallel network. But when we have multiple sources, 2 or more sources, a better approach is what we're going to use. Series and parallel will fail us. So we'll use the Kirchhoff's law or Kirchhoff's approach. So let me quickly restart the meeting and we begin with Kirchhoff's law. Thank you.